This is part 7 of the Module 10 lecture. And here we're going to talk about the inferences about a single population variance. And this is covered in section 11.4 in your textbook. All right, to review what we have done in terms of the different chi-square tests, we already looked at the two chi-square tests when we're working with a discrete variable. We looked at the goodness of fit test, and then we look at the test of independence or homogeneity. And in both cases, we're dealing with a variable type of discrete data. In this section, we're going to now talk about a continuous variable, and we're going to talk about the inferences about the population variance. So we're looking, in this case, at a continuous random variable. Now, inferences about the variance, these are, at least in my own personal experience, the way I encountered this is in the continuous improvement world of industrial and service processes, because the objective there most of the time is reduce variability. For example, when we're looking at the capability of a process, we want to show that the standard deviation of the characteristic of interest of a particular product is sufficiently small to ensure that every unit of product meets the customer specifications. I don't know if you have heard of the Six Sigma goal or management tool, and that's what we're looking for. Reduce the variability to such a point that the likelihood of having a product whose characteristic is outside the specification limits is 1 in a million, for example. Another example is when you're evaluating a measurement system. So you're a system that measures some characteristic on a product. And one of the goals when you evaluate the measurement system is to show that the system's precision is small enough so that that variability of the measurement instrument does not contaminate the actual measurement of the characteristic of the product. So I encountered these inferences in both of these cases, and and I'm sure it's present in other situations. But this is where I've seen personally the need to make inferences about a variance. When we say the inferences of variance, at this point, I think you realize that we're talking about two things: constructing a confidence interval or testing a hypothesis about a population variance. And because we're making an inference about the population variance, well, we're going to rely on the sample variance to make the inferences. And to calculate the sample variance, we use this equation, and you might remember this from Module 3. That's where we looked at this formula on how to calculate the sample variance. Here's an example that we're going to solve. And in this case, this comes from where my wife used to work. And this is in a high volume pharmacy operation where the variability of the variability of the cycle time to fill a prescription from the time that they receive the order to the time that they deliver it, the cycle times vary so much that they are seeing 7.3% of these prescriptions having such a long cycle time that they end up being delivered after the expected or the required date. So they are late in their deliveries. So in order to meet, and also a common initiatives, what they call the 5 nines, where you want 99.99% of the prescriptions to be delivered in time. So in order to do that, you need to reduce the variability, and they have already done the calculation, and they have determined that the variance must be less than 20.25 minutes squared. Remember, the units for the variance are squared. Or if you want to talk in terms of standard deviations, that standard deviation has to be less than 0.45 minutes. All right, so management conducted several improvements to reduce variability, and they decided to see how much of an improvement they actually achieved by what they did. So they measured the cycle time of 31 randomly selected prescriptions, and now this data is in this Excel file called Pharm cycle time. Now, they want us to determine if the variance of the cycle time is 20.25 or less at a 0.01 significance level. And this is the required variance to meet the 5 nines initiative goal. And they also want us to calculate the 99% confidence interval. All right, to do this, we're going to follow our trusty hypothesis test process with the 5 steps. And so we're going to look at how we state the null hypothesis, what distribution we're going to use, how we calculate the test statistic. And then once we have the test statistic, we can find the p-value or the critical value, and then make a decision about the null hypothesis, just as we have done before. All right, and here we have all 3 directions of the test. So you have the two-tailed test, where you would like to show that the variance matches some specified value. This sigma square sub 0, this is the value under the null hypothesis. So under two-tail, we want to under the alternative hypothesis, we want to show difference, that the actual variance is different from some specified value. Under the null hypothesis, that variance is equal to the specified value. If you have a right-tailed test, then under the alternative hypothesis, you're looking to show that the variance is larger than some specified value. Under the null hypothesis, the variance is less than or equal to that hypothesized value. If you're working with the left-tailed test, then under the alternative hypothesis, you're trying to show that the variance is smaller than some specified value. And then on the null hypothesis, the variance is actually larger or equal than some hypothesized value. All right, so these are the 3 possible directions of the test and how you will express the hypothesis for each type of test. All right, the test statistic now is defined in terms of the sampling distribution of the sample variance, and is given by this test statistic, which is n-1, the degrees of freedom, times the sample variance divided by the population variance. So this test statistic, if the sample comes from a approximately normal distribution, will follow a chi-square distribution with the degrees of freedom of the number of observations minus 1. So we'll be calculating the degrees of freedom exactly as we did for the t-test in module 8. So is the number of observations minus 1 for this form of the test statistic. All right, so if we decide to use the critical value approach to make a decision about the null hypothesis, then we're going to use table 6 with the significance level and the degrees of freedom of n-1. And again, if the test statistic is in the rejection region, we'll reject the null hypothesis. The same rule as before. Now, if you have a left-tailed test, well, the rejection region is to the left of this alpha minus 1 value. Remember, I'm using 1 minus alpha because in table 6, it gives you probabilities to the right. And so that will be the distance from this x minus 1 alpha square to 0, because remember, the chi-square stops. The values of the chi-square distribution stop at 0. So the rejection region will be on the left side. And that's what I'm showing right here. If you have a right-tailed test, then the rejection region will be on the right tail of the chi-square distribution, and that will be the chi-square alpha, because now because table 6 is giving you probabilities on the right side. If you have a two-tailed test, and as before, we have 2 rejection regions, one on the left tail and one on the upper tail. And to find these critical values, we have to divide alpha by 2. The upper value will be at alpha divided by 2 with the degrees of freedom of n-1, and the lower value will be at the 1 minus alpha over 2 with degrees of freedom of n-1. Again, you find that in table 6. If you decide to use the p-value approach, well, again, if we have a two-tailed test, we're going to use 2 times the probability to the right of the observed value of the test statistic. And if you want to use Excel, here's a formula that you can use. If you have a right tail test, then we have the probability to the right of the observed value of the test statistic. And here's a formula to find that p-value. And if you have a left tail test, then the p-value is the probability to the left of the observed value of the test statistic. And if you want to find the exact p-value, here's the formula. And the decision is the same as before. If the p-value is less than alpha, we reject the null hypothesis. All right, so now we've laid all the elements that we need to perform a hypothesis test for a one population variance. Now, if you like to calculate the confidence interval, then again, if the sample comes from a normal distribution, then the 101 minus alpha % confidence interval is defined like this, and now you recognize this as part of the sampling distribution of the sample variance. And see, the lower confidence interval limit is the degrees of freedom times the sample variance divided by the upper chi-square value. And the upper confidence interval limit is the degrees of freedom times the variance divided by the lower critical value. So notice that the chi-square values are crossed. So the lower confidence interval limit uses the upper critical value, and the upper confidence interval limit uses the lower critical value. So keep that in mind so that you don't mix them up and you end up making a mistake. To find these values, well, you have to find the upper value, you divide alpha by 2, and with the degrees of freedom of n minus 1, you find the upper value. To find the lower value, you use the degrees of freedom of n minus 1 with 1 minus alpha divided by 2. All right, so that's how you will calculate the confidence interval limit. So I'll stop here. In the next recording, we will perform a hypothesis test for a single variance, a single population variance, and calculate the confidence interval for one population variance.